Welcome back to AGRON Info Tech. In the previous tutorial, we explored categorical survey variables using weighted tables and plots. Now we switch to quantitative survey analysis, and we use body mass index, or BMI, as our example. The goal is simple. Estimate what BMI looks like in the population, not just in the sample. I start by loading the packages we need. NHANES brings in the dataset. Tidyverse helps with data wrangling and plotting. Survey is the key package that understands weights, strata, and clusters. Broom is here, so we can later turn model outputs into clean tables, even though today we mainly focus on summaries. Right after that, I set one important survey option for lonely PS use. Sometimes a stratum ends up with a single primary sampling unit after filtering or missing data. Instead of throwing an error, this option tells R to use a reasonable adjustment so the analysis can continue safely. Now I load the NHANESraw dataset. This is the public health survey we've been using in this project. Before we build the design, I create a 4-year weight. NHANES provides a 2-year examination weight, and because we're treating this as a combined multi-year sample, I scale the weight by half. This keeps the population totals consistent for the combined period. Now comes the core step. I build the survey design object. I tell R which data frame to use, and then I specify the design variables. I set the strata variable so variance estimation respects the stratified sampling. I set the PSU identifier so the clustering is handled correctly. I also turn on nesting so the PSU structure is treated properly within strata. Finally, I provide the weight variable so every estimate we compute reflects how many people each participant represents in the population. At this moment, the analysis shifts from plain data analysis to design-based survey analysis. Now I compute the unweighted mean BMI first, just to see what we get if we pretend this was a simple random sample. The output shows an average BMI of 25.6. This is a straightforward sample mean, and it ignores the survey design entirely. Next, I compute the survey-weighted mean BMI using the survey design. I also tell the function to remove missing BMI values so we don't lose rows unnecessarily. The output now give a weighted mean BMI of 26.634 with a standard error of 0.101. This immediately tells us two things. First, the population estimate is higher than the naive sample average. Second, we now have a design-correct measure of uncertainty, which is crucial for real reporting. Now I add a confidence interval for that weighted mean. The interval runs from about 26.44 to 26.83. This range is the believable window for the population mean BMI once the survey structure is taken seriously. This is exactly the kind of result you want when you're writing conclusions, because it combines an estimate with honest uncertainty. Next, I move from averages to quantiles. This is useful because BMI is not perfectly symmetric, and percentiles often communicate the distribution better than a single mean. I request the 25th percentile, the median, and the 75th percentile using the survey design, and again, I remove missing values. The output shows the first quartile around 21.60, the median around 25.93, and the third quartile around 30.73. Each quantile also comes with uncertainty, which tells us these are not just sample percentiles. They are population percentiles with survey-based standard errors and confidence intervals. Now I visualize the distribution using a survey-weighted histogram. I filter out missing BMI values, and I map the weight into the plot so the bars represent population scale rather than raw counts. I also choose 40 bins so the shape is smooth without becoming noisy. When the chart appears, the distribution peaks around the mid-20s and then stretches into a long right tail. That long tail tells us that a smaller fraction of the population has much higher BMI values. And because the histogram is weighted, that pattern is meant to reflect the population, not the sample. Next, I compare BMI between genders using a survey-weighted group summary. I use a function that calculates the mean BMI within each gender while still respecting the full survey design. The output gives a weighted mean BMI of about 26.84 for females and about 26.42 for males, along with standard errors for each group. The difference is not huge, but it is visible, and the standard errors remind us that we should focus on the estimate together with uncertainty. Now I turn that table into a clean format and compute a 95% confidence interval for each gender using standard error. The resulting table shows females roughly from 26.6 to 27.1, and males roughly from 26.2 to 26.7. This gives us a simple, teachable summary that is easy to communicate. Finally, I plot those gender-specific means with their confidence intervals. The point marks the weighted mean for each gender, and the vertical error bar shows the 95% confidence interval. When you look at this plot, you can quickly compare both groups without reading a table. You can also see how much the uncertainty overlaps, which helps you avoid overclaiming small differences. At this stage, we have a complete quantitative survey exploration workflow. We estimate a population mean, we add uncertainty, we summarize the distribution with percentiles, we visualize the weighted shape, and we compare groups correctly. In the next video, we take the same survey design and move into modeling. We fit a survey-weighted regression model and interpret the coefficients as population relationships, not just patterns inside the sample.